good evening, and thank you for joining us at this, the 8th lecture of our special 50th anniversary inaugural lecture series. What an anniversary year it is turning out to be. I'm Professor Josie Fraser, Deputy Vice-Chancellor here at the Open University, and I'm proud and privileged to be hosting one of the university's 50th anniversary celebration events. These events showcase our research, teaching and knowledge exchange portfolios. Each year, the Open University's Vice-Chancellor invites newly appointed and promoted professors to give an inaugural lecture. Over the course of a year, our inaugural lecture series provides an opportunity to celebrate our academic excellence, and each lecture represents a significant milestone in an academic's career. This evening, we'll hear from Mark Brandon, Professor of Polar Oceanography, on his topic of the polar oceans and global climate. It is very apt for Mark to deliver his inaugural lecture during our 50th anniversary year, given that Mark's research has attracted millions of viewers because of BBC co-productions like Blue Planet 2, Frozen Planet, Earth from Space and Coast. This relationship with the BBC spans the whole of our 50-year history, and academics like Mark keep that relationship alive. Mark has over 25 years' experience of leading successful large projects in both research and teaching. He's currently the Associate Dean for Enterprise and External Engagement, responsible for coordinating and leading our free learning offers and broadcast right across the Open University's Faculty of Science, Technology, Engineering and Mathematics. Mark won the 2012 Times Higher Education Award for Most Innovative Teacher of the Year and has won a further 4 Open University Teaching Awards, no mean feat. His main research interest is the polar oceans and the physical processes that happen in them. Mark has had a particular strength in cross-disciplinary work, and he uses robotic and remote sensing technologies. He's delighted to get the opportunity to talk about polar science wherever he can. Mark also holds a number of external appointments. He is the current chair of the Programme Advisory Group for the Natural Environment Research Council programmes that comprise the bulk of the current UK Antarctic oceanographic field research, and he is a core member of the Natural Environment Research Council's Peer Review College, which allocates grants in the field across the UK. Intriguingly, Mark is also a member of the Antarctic Place Name Committee, which I am told is responsible for naming unnamed locations in the British Antarctic Territory. Mark is also a leading member of our environmental science curriculum development team. It gives me great pleasure to introduce Professor Mark Brandon.
Well, thank you very much. I'm not used to getting claps at the beginning. So this is probably the lecture that I've rewritten the most times of all the lectures I've ever written, and I asked people how should I approach it, and one colleague who I really get on with well said, put up some hero shots of you and then talk about what you did. Well, if I did put that up, my children and my partner would look at it and say, well, you don't look like that very often, so we can't really use that one. So I started my research at the British Antarctic Survey. Before the British Antarctic Survey, I was at the Scott Polar Research Institute. I've always been interested in the cold as a kid, always. I can't really explain why that is, but it's a physiological thing. I didn't realise how unusual it is to be able to concentrate and work in -40 until I did it and found other people struggling. But for my PhD research at the Scott Polar Research Institute, I would be dropped off by a helicopter on the ice, and then this picture is frozen ocean. I drilled through the frozen ocean and dropped sensors underneath. And what I was interested in is when the ocean freezes over, the salt at the surface of the water gets squeezed out of the ice crystals. It makes the surface of the ocean more dense and it sinks. If you're working in the Arctic, it's a pretty dangerous place to be. And what we found, of course, is that if you smell interesting, there's all sorts of things that want to come and find you. And I often get asked the question, as someone who's worked a lot in the Arctic and the Antarctic, which one do you prefer? And I have to say I prefer the Antarctic, because a British person, if you're having to carry around a gun, that makes me feel uneasy. But you see the black dot on the left-hand side of this picture? That's the bear guard in the distance taking photographs. And you can see the rifle balanced carefully on a milk crate, pointing safely away from people. So that was my PhD research. Then I was really fortunate to get a job with the British Antarctic Survey in Cambridge. In the British Antarctic Survey, I worked in a cross-disciplinary group working with biologists and chemists, as well as physicists. I'm a physicist myself. And so I got to learn a lot about the ecosystems around Antarctica. This picture is the ship that I worked on a lot, the James Clark Ross, and it's at South Georgia, which is, I'll come back to South Georgia later on, but it's the centre of the most amazing ecosystem. While we were working around South Georgia, it turned out that I met lots of production companies, and the production companies, I found myself constantly answering questions from people saying, what does this mean? What does that mean? And these are all programs that I'm proud to have been associated with, really proud. And I don't know if I've got any special talent. I think my ambition is not to be the person in front of the camera. I'm very happy helping other people. And so helping people produce these things was a really good thing to do. The one that I enjoyed the most, I think, so far in my career has been Frozen Planet. And I say Frozen Planet instead of Blue Planet 2 because Frozen Planet was about the things that make my heart sing, which is the frozen seas. So I'll start off with episode 7 of Frozen Planet.
This white wilderness, this emptiness, is the North Pole. I'm standing in the middle of a frozen ocean. Beneath my feet, and for over 500 miles in every direction, there are several meters of ice. But something significant is likely to happen here at the North Pole soon. Chances are that sometime within the next few decades, perhaps even as soon as 2020, there will be open water here for the first time in human recorded history. The Arctic and Antarctic are changing. Enormous masses of ice that have been frozen for thousands of years are breaking apart and melting away. Ice scientists are...
So looking at your faces now, I should have just left the episode on. But the thing to point out about that is all of these statements that Sir David was making about the climate and about how the planet's changing, all of those are built on research, and all of those are built on people like me, other people in the OU, and other scientists around the community that contribute to these programs. Now, while the final edits were going on for Frozen Planet, Sir David made this statement in the newspapers. And what I think it kind of baffled people, because certainly in his case, he really doesn't know everything. But I think what he was saying was the difference between someone who is a presenter and writes things and someone who stands with the academic community on stuff that is fully based in research. And I think that's why there's so much traction in these magnificent programs. Now, why did the Open University get involved in broadcast? Well, obviously, we as a university that was connected with broadcast right from the very beginning, nowadays we make these large co-productions, and we use the co-productions in our teaching materials as well. So I thought I'd show you quickly what sort of things it takes to do a shoot with Frozen Planet, and something I had to do in relation to a course that I worked on with colleagues. This is the number of people it takes on a shoot, and that's in Svalbard. And if you look at this picture, you can see me doing the sorts of things that OU academics do in the Arctic. That's Sir David sitting in his deck chair eating a bar of chocolate. And he was, they were lining up the camera shot. When you go to a great place like that, it's very important that you go and get your picture taken with Sir David. And it's not, I very much like working in the background. It's not really my thing, but everyone said, oh, you have to go and get your picture taken with David. So I kind of sidled up to him and said, while they were lining up the camera, David, I'm really sorry, this isn't really my thing. And he just leant over and said, I'm starting to feel a bit like a lamppost with dogs coming up. He has a very good sense of humour. But that effort, all of those people in the field and all of that effort to get there, we went out on the Skidoo and it was like 3 hours in -20 to get there. It's very sunny, which is why it doesn't feel cold, and there was no wind. So David flew out in a helicopter. I'm going to show you the clip from that episode that made it into the final series.
This is the front of a glacier, quite a small one, believe it or not. Glaciers are like rivers of frozen fresh water flowing across the surface of the land. This one, like most polar glaciers, is flowing down from a vast inland ice sheet. And it's what happens to those ice sheets that could radically alter the face of the planet.
So if you think about that clip, what he's just said about that glacier is something that can be used in schools, in our courses, all the way through to describe what was happening with climate change in glaciers. And that sort of component used in our teaching materials is what we can carry through. Because I had the good fortune to write a course at the same time called The Frozen Planet, it was linked to the CV series. Part of the deal of me having the pleasure of going to the Arctic with the BBC was I had to do some filming. If you ever think you're good at science presenting, wait till David Attenborough sits down in his deck chair, opens a bar of chocolate, and the BBC say it's your turn. It's the same beautiful location, lovely glacier.
I'm standing on the sea ice in front of Turnberry Glacier.
Yeah, that's enough of that. Okay. But lots of these filming that we did, it got made part of course materials as well. Now, also linked with the broadcast projects, in particular this year, we've had Earth from Space, we've had Blue Planet Live, and the Planets, and all of those programs had print items with them, and people phone up, they go to the website, they request them. This was an A0 poster we did with the Arctic. On the other side is the Antarctic. There are some outside, help yourself as you leave. But the real point is, as well as getting lots of pretty map out, we're getting lots of science information as well. So, and that's packed in, and we use that in the course materials too. So a bit about the science now. This is a picture of the Arctic. Now that sort of flat bit in front of you is frozen ocean. That's kind of my thing. The bit in front that looks quite rocky, that's glacial ice. That's pieces of freshwater ice that's frozen in. And then there's snow on top of it. And you can see the sort of road, that's our skidoo tracks to get there. That's the Arctic. Now, if I show you a picture of the Antarctic, it's got the same sorts of things in it. Same frozen ocean, same mountains, the same glaciers, and the same bits of ice in there. And you would be hard pushed to tell the difference from two photographs between the Arctic and the Antarctic. But they are fundamentally different places. In the Arctic, on the left-hand side, you've got an ocean that's surrounded by land. In the Antarctic, you've got land which is surrounded by an ocean. And those two regions, and the fact that one is land with ocean, the other is ocean with land, completely control, in my professional opinion, our climate and our planet. Now, the difference between the ocean and the atmosphere, I've got two temperature plots here. You've got month of the year on the horizontal axis. On the vertical axis, it's the temperature. If you look at the black one first, if you look at July, which is where we are now, it's the height of summer. In Alert in northern Canada, it's just above 0. As you're going down into autumn, you see the temperature is going to fall to about -30 degrees, and then back up into the following spring, and the temperature will rise. But you get this nice, smooth increase in temperature and then a fall in temperature. Now, if you look at the red line, that's the South Pole station. Obviously, in the South Pole, it's the seasons, the opposite time of the year. But in January and December, you've got the Antarctic summer, so -30 at South Pole. But instead of having this nice, smooth seasonal cycle of temperature increasing and falling, the temperature drops in winter, stays really flat, and then rises at the end. And where it's relatively flat from March through to September, that's basically as cold as it can get. And it's not going to get much colder unless something strange happens with the weather. So in our courses, we teach about how it gets cold and why it gets cold in the polar regions. I know it's a stupid question, you might think, but why is there ice in the Arctic? And I'm going to show you a couple of clips from our teaching materials that they made me film and see if my children recognise anything in this.
So what I've got in my hand is a torch connected to a pipe with a bit of tape. Now all I'm using this torch for is to be my sun. and the pipe is just going to project the sun into a circle. And this football is going to be my Earth. So you can see that at the centre of the football, I'll call it the equator, we've got a nice circular pattern coming from the torch. And that circular pattern is the energy from the sun. Now at the equator it's a nice round circle. But as I go up my football up to higher latitudes, you can see the shape of the circle changes and it starts to get more and more smeared out. By the time I get to very high latitudes, you can see that it's really diffuse over quite a wide area. But the torch is only putting out the same amount of energy into that space. So the energy from the circle at the equator is smeared out over a much wider area. And that means that the energy that reaches the surface of the Earth is greatly reduced at high latitudes. Now there's another thing that reduces the amount of energy that reaches the surface of the Earth at high latitudes. The distance between my finger and thumb is going to be the thickness of the atmosphere. So now my solar energy reaching the surface of the Earth is passing through a thickness of the atmosphere. Now over the equator it falls directly on the surface, but as we go up to higher latitudes, effectively the thickness of the atmosphere is getting bigger and bigger because the sunlight is grazing the planet. So by the time we get up to higher latitudes, there's a much greater amount of atmosphere that the sunlight has gone through. But there's one more reason the solar energy is reduced at high latitudes, and that's to do with something called the albedo. And we'll talk about that on the module website.
And so from the module website, you get reduced solar energy at the polar regions because the light is more diffuse and it's passing through a thicker layer of atmosphere. And then because the ground is white, most of the energy that arrives at the surface is instantly reflected back out to space. On the left-hand side, if it falls an ocean, then almost all of it is absorbed. And these sorts of things, we get our students to do this with, go and put your hand on a black car and a white car on a warm day. Those sorts of things to see what albedo does. So that tells you why the solar energy is reduced at polar regions. How to do the seasons? Well, when I was in Svalbard, I thought of doing something with an orange. It was frozen. It's very cold in this film, and you can tell it's cold because I've still got my hat and gloves on.
Anyone that doesn't live at the equator will already be familiar with the seasons: winter, summer, autumn and spring. Now with the help of my skidoo helmet, this frozen orange, I'm going to show you how that works. The skidoo helmet is my sun. Now if that really was the size of the sun, the Earth would have to be about the size of a pea, and I wouldn't be able to show you this. So I'll use an orange. Now my Earth has a North Pole and a South Pole at the bottom. And to make that more visible, I'm going to use this pen. Now I'll put my Earth there. So the Earth is rotating once every day. And things on this side of the Earth are in sunlight, so this side it gets day, and this side it gets night. Now the axis of the Earth's rotation isn't actually in this direction. It's inclined at an angle to the sun. Now that angle to the sun means that in the northern winter, like we are now, the Antarctic is closer and pointing towards the sun. So the Antarctic gets more solar energy, it's warmer. In the north, it's pointing away from the sun. So there's less light coming in here. The days are shorter and it's much colder. But 6 months later, it's completely different because the Earth has orbited around the sun. And now, the North Pole is pointing towards the sun. So this is where you get the long days. And the South Pole is pointing away and the Antarctic has the short days. Above the latitude of the Arctic Circle in the north, it's daylight all the time. So on this island at 78 degrees north, in a couple of days' time, the sun's going to come above the horizon, and it's not going to go down until, I think it's about the 20th of August. It will be what we call polar day. As the sun gets higher in the sky, all of the snow you see behind me will melt fairly quickly, and the plants and the insects will reappear. And there's just a short window for the other animals, birds such as fulmar, reindeer, even polar bears, to grow and reproduce before the Earth orbits around the sun again and polar night comes once more.
So those reasons are why we end up with super cold temperatures in the Arctic and the Antarctic. So what does that mean on the ground? Well, snowfall, which is fresh water, falls down from the atmosphere, lands on the surface. If it doesn't melt during the summer, it builds up huge thicknesses of snow. In between the bubbles, in between the snowflakes, you get bubbles of gas, which is the atmosphere when it fell. When the snow fell, you can see the bubbles in the ice there. And this snow develops ice sheets on land that are kilometres thick. In the case of Greenland, 3.5 kilometres, Antarctica, 4.5 kilometres. That's the surface of Greenland. And so if you look at a picture of Antarctica, you often see these pictures where it looks kind of white. But if I put colours on that, which more traditionally you see on maps, you can see the contours or height contours in there. If I draw the contours in, so the snow falls on and it builds up these sort of these high points and low points, and then the snow, once it's formed to ice, it starts to flow, and it flows in glaciers. And that could be best summed up in this film from NASA. Now, the data that made this movie of the glacier flow in Antarctica comes from satellite data, so it's all been detected. Where you've got purples and reds, it's got very high velocity or relatively high velocity ice flow, and where it's the sorts of yellows, it's slow. But the ice is flowing away from the high points towards the coasts. Now, what happens when this snow, this freshwater ice, reaches the coasts? You end up with these ice walls like this. This is the edge of an ice shelf. So the Open University is justifiably famous for getting students to do experiments. So we can't do experiments unless we do them in our own kitchen. So what is going to happen when that ice reaches the ocean? Well, the first point to make is in this experiment. And the point pretty quickly is that the fresh water, the ice that's in the water is going to melt much quicker than the ice in the air. So increasing temperatures in the Antarctic, increasing atmospheric temperatures are really important, but most of the melt that's happening on Antarctica is where the ocean is in contact with the ice. I'll come back to that. The next point is when this ice melts, where does it go? And that's in this experiment. I've got 2 cups of water, 2 ice cubes, and as the ice cubes melt, the dye in the ice will show you where the meltwater goes. One of the water is fresh water, the other one is salty water. And as it speeds up now, you can see the melt. And where you've got salty water, when the ice melts on it, it forms a lid on the surface of the water, whereas in fresh water it mixes all the way through. Of course, the ocean's salty, so where these icebergs drift away from Antarctica, they affect the density of the surface. Now, this is a fantastic movie showing the drift of all of the known large icebergs from Antarctica. Now, you've got year ticking up, and each colour, the colours around the edge of the continent indicate where the icebergs fractured off. And you can see that as they're being detected, they're being tracked out. Now, as we go on in time, better satellites have better resolution, so you see more icebergs that are smaller, or they're still pretty big. And you can see huge flocks of them coming through. There was a big ice shelf that broke up in 2002. But if you look at the green ones, you can see there's kind of you could call it a hotspot of icebergs drifting away from Antarctica. As we come through to modern day, and that's all of our icebergs that we've detected so far, the large ones. The small ones, satellites don't pick them up so well, and there are zillions of those anyway. But this is this island where the ship, I showed you the picture of the ship earlier. South Georgia is about 120 kilometres long. So this is one of these icebergs. This one was called A34 from 2004, which drifted up around South Georgia. Now, a point to make is I've showed you Antarctica. I could have shown you the same sorts of images from Greenland. The same sorts of data exists. The reason I showed you Antarctica is because things like iceberg drift looks much cleaner when it's in the oceans, but you can make the same maps and researchers have the same beautiful maps of glacier flow. So that's snowfall that falls on land, so that's fresh water. You know, ships can pull up to icebergs and take on fresh water. The old explorers used to take pieces of iceberg, melt them and use them for fresh water. The other part of the system, which I've done a lot of work on, is when the ocean freezes, which was what my PhD was on. You can see the date ticking up, and for each plot, Arctic on the left, Antarctic on the right. It's the same day in each image, and you can see that as we go towards the summer, the sea ice in the Arctic is decreasing, but the sea ice in the Antarctic is increasing. Now we're coming up to the Arctic minimum, which is around September, and we're past the equinox, and the Arctic ice starts to grow again, and then the Antarctic ice retreats. So if you were in space and you were looking at this for the Arctic and the Antarctic, it's a bit like the heartbeat of the planet. If there were no clouds, it would be really obvious. But as the ice is growing out, if you think about the ice crystals that are squeezing out the salt from the ocean, it's making the surface of the ocean more dense, and that ocean water is sinking. So every time the ice is growing out, it's creating dense layer of water at the surface, and that water is going to go somewhere. I'll come back to that. One other point about the sea ice is it's a fantastic habitat. Where there's sea ice, things live, and these are crab-eater seals. Where you've got seals, you've got things that want to eat the seals, and then you see lots of penguins as well. But the thing that ties all of those animals together in the sea ice are the krill. Now, krill is an animal you may have heard of. It's a bit like a prawn. They actually taste quite nice if you get them straight from the sea, but don't eat too many. They've got quite high fluorine in, I believe. But yeah, so the different animals eat the krill, and that's a part of the food web. So if you take a particular seal, this one is a crab-eater seal. The teeth of this mammal are the most highly evolved of any mammal's teeth. So it'll take a mouthful of the seawater near the seaway, use its tongue to squeeze out the water and end up with a mouthful of krill. And the whales have adapted to exactly the same sorts of thing. You can see my foot in the picture here. I was quite excited. That's a humpback whale, and it's got like baleen, a comb, which you might have heard of, which was used in women's corsets in the old days to extract the krill. But then it's a sensible question to ask, what do the krill eat? And if you look at the krill, you can see that there's all these greenish pigment, and the pigment comes from the algae that's in the water. And the algae is in the water, you might have heard of plankton blooms in the ocean. Well, as the ocean freezes, that stuff ends up in the ice as well. So it's very easy to think of sea ice as being a fantastically pure and pristine environment. The reality is sometimes when your ship is going through the sea ice, it's literally like going through chocolatey water. So one of our big breakthroughs, my first big breakthrough in my career actually, was sending a robot beneath the ice of the Antarctic. And we were the first people to detect large swarms of krill beneath the ice. And the robot on the left is a forerunner to what was Boaty McBoatface. In those days, we didn't have any imagination, so we called it AutoSub, which is... As I said, I like to work behind the camera rather than... So go back to that heartbeat, the heartbeat of the ocean, the sea ice. It's making this dense water. Time for another experiment. I've got cold, salty water that's coloured blue, and so that's going to sink. And I'm going to put in some warm, salty water. And I'm a bit clumsy, so it gets a bit mixed up. And I think someone's recognised our kitchen implements there. But you can see the red water is rising, the blue water is sinking. Think about that in a planetary sense, where you've got polar oceans, cold, dense water is sinking in the polar regions. In the equator, you've got water that's warm and it's less dense. And I'll use this schematic, which is a famous one, which shows this idea of the Great Ocean Conveyor Belt. Now, this conveyor belt is an idea of heat being moved around the planet. And I can show you what that's like. If I show you the temperature in the ocean measured along that yellow line. So this is a cross-section where a ship has made these measurements. At the top panel, I've got latitude on the horizontal axis and depth of water. Antarctica on the left, Greenland on the right. And you can see that the purple water, which has been generated as the sea ice grows, sinks and falls away from Antarctica. And in other places like the equator, where the water warms up, it creates these huge horizontal currents and this overturning circulation. The purple stuff's really important because something I haven't talked about at all is carbon in the atmosphere, and I'll come back to this. CO2 in the atmosphere is absorbed in the ocean, and it's mostly absorbed in a few specific parts of the ocean. And it turns out the Southern Ocean is where most of the carbon dioxide, it's the biggest sink of carbon dioxide at the moment. And so that is pulling carbon dioxide down into the centre of the ocean. Is the ocean circulation important for us? Well, absolutely yes. This is a satellite map of sea surface temperature, and you can see that around Britain it's nice and warm. So if you go up to northern Scotland, these pictures are taken at the same time of the year. It's quite a nice climate. If you go to the same distance from the pole, the same latitude at Cape Farewell in Greenland, it's horrendously ice covered. So these ocean currents are hugely important in our local climates. But I've shown this projection, and as a polar scientist, this projection bothers me a lot because it's a Mercator projection and we get this weird idea about how important the polar regions are. You get this idea that they're really big and that they dominate things. Actually, a nicer way to think about the Earth is in this picture, where I've got sea surface temperature as colours, where the Arctic and the Antarctic act as two sorts of opposing nodes of the circulation, really. And they kind of link everything together. And there is a global ocean circulation, and if you throw radioactivity from a nuclear power station in Japan, that radioactivity is getting transported around the oceans right now. So I've said that the ocean circulation affects the temperature of, close to Britain. It also affects the temperature around Antarctica, which is this really critical thing. On the left-hand side, that warm water comes into contact with Antarctica. So you can see in this map as we zoom in, that's the velocity map that's showing you where the ice, the strong currents are in the glaciers, and that's the cross-section. We've got the seabed in there as well. And warm water is flowing towards Antarctica. It comes in contact with the ice and it's causing melting in those regions. But because you're melting the ice in those regions, that means that the ice surface lowers. And Britain, in Leeds University, Centre for Polar Observation and Modelling, are world leaders in measuring this sorts of things. And their research generates maps that are showing how much the edges of Antarctica are lowering. And we can do the same thing with Greenland as well. Where you've got those large circles on the right-hand side that are red, that's the parts of Antarctica where they're melting fairly rapidly. My connection to this sort of thing is I'm one of the few hundred people that spent time in Pine Island, this place where Antarctica is melting the most. And we measured how much heat was flowing towards Antarctica through the ocean and how much it was responsible for melting the ice. But coming back to teaching, I've talked about the krill and the sea ice and how the krill are distributed. This is a map put together by Angus Atkinson from Plymouth Marine Lab showing the distribution of krill around Antarctica. And you can see again, you've got that big patch up near this island that I worked at, which was South Georgia. And if we zoom into South Georgia, you'll see something special about that island. South Georgia was the centre of the land-based whale industry for the UK, and that's an old whaling station. This is a picture of it a few years ago, and you can see the ramp in the middle of the picture there is what's called a flensing ramp, where a flensing plan where they would tow the whales on and cut them up, and then they would take, that's the boiler shop basically, where they would boil the whale bits down. So we use this stuff in our course. So when we talked about Frozen Planet in the course that we wrote, linked with it, as well as talking about the climate and the ecosystem, we talked about how we exploited the ecosystem. And this makes the point really. The picture on the right-hand side is a famous data set from showing the catch of blue whales around South Georgia in just 1 month of the year in 1926. Now, I worked around South Georgia for nigh on a decade, and I've seen one blue whale, and that's the numbers of blue whales caught in just 1 month. The picture on the left is a watercolour of the researcher to show what it was really like when they were cutting up the whales. So how can you use that sort of stuff in teaching? Well, what we did was use it to teach basic mathematics. So we taught the students about whales. If you can tell them how many barrels of whale oil you can get out of each individual whale, you can work out how much a whale is, how many barrels of oil it creates, how much value for each whale. Then you can calculate how much that money from Edwardian times and from the Victorian times would be worth today. And the students work it through and they come up with a number from 1 month or 1 year of one species of £150 million worth of whales from South Georgia. And that's just for one species. The blue whales, they also caught several thousand, well, you can see in the overhead, several thousand other species as well. So suddenly the students get it, that there's this real thing that they can do and they can understand why whaling is happening linked with the science as well. Another thing which we did in Frozen Planet, which was particularly brilliant, pointing out how cool modern tricks that we can use in terms of teaching. This is just Google Earth, and we wrote a front end on it. And as you zoom into Google Earth, you can see those sorts of dirty brown colours that are in there. Those sorts of rocks are icebergs, the flat bits are sea ice, and the dirty brown colour emperor penguin colonies, and the emperor penguin colonies hide in the ice. And this was just as this work got published. Of course, in the OU, we've got a fantastic online library. So with level 1 students that are just starting to learn and how to learn things and how to understand, and we can send them to the library to track down, guided of course, but the research articles that found this data set, which is kind of really cool to expose them to that sort of thing. And because I'm a geek and I love polar history, we also taught them about the famous things in polar history, the worst journey in the world. And of course now there are classic libraries that have scanned the original first edition, so you've got easy access to these wonderful things. So when Frozen Planet came on, that was a revelation that you could see penguins from space. Did anyone watch Earth from Space this year? This is what appeared in Earth from Space.
This new technology is now helping wildlife conservation in the most inaccessible places. Antarctica. A continent so hostile and remote that studying life here is incredibly challenging. But now, satellites allow us to access every square kilometer of its surface. And this has led to an extraordinary discovery. Brown patches dotted across the ice. Seemingly out of place, but they are vital clues, helping us to find one of our most iconic species.
That's enough of that. People who haven't been bitten by penguins like them more than people who have. But being involved in and co-producing programs like Earth from Space, again, linked to our teaching and using it for course materials. So where are we going? I talked about carbon a bit. Nowadays, the accessibility of data is amazing online. This is, I had to hand these slides over a week ago, but this is the carbon dioxide in our atmosphere from Hawaii for a week last year, and we're at 413 parts per million. Now, they started measuring carbon dioxide in this location back in 1958, and since 1958, it's steadily increased. There's a wiggle on it, and that wiggle is in the Arctic summer, plants grow. So you've got the bottom axis there goes from 1958 to today. If we go back in time a bit further, this is back to 1750-ish, 1700, which is the Industrial Revolution. So all that time, our industry is going on, we're putting carbon dioxide into our atmosphere, and you can see that carbon dioxide has increased. Let's go back to 10,000 years now. The red shading is the most recent bit. 10,000 years is a really interesting time period, because that's basically the time period that all human civilizations have formed. Slowly, carbon dioxide has risen in our atmosphere, but you can see now, since the Industrial Revolution, how steep that rise is. If we drill down into ice cores in Antarctica, you can get back now to 1 million years. This is stuff from on their website, which goes back to 800,000 years ago. And you can see there are wiggles in this line. There are times when the carbon dioxide in the atmosphere is low, times when it's high. When it's low, atmospheric temperature is cooler, and you end up with these ice ages that you will have heard about. 20,000 years ago, when carbon dioxide was low in our atmosphere, most of Britain was covered, or large parts of Britain were covered by a large ice sheet, which has disappeared since then. When carbon dioxide in our atmosphere was high, well, then it's warm periods. And it's worth pointing out that at the moment we're up here. As the carbon dioxide in the atmosphere has increased, what's happened to the atmospheric temperatures? Atmospheric temperatures have increased pretty much in line with carbon dioxide in our atmosphere. Now, when I started working in the polar regions, it was a bit of a backwater. It was a place that people weren't really too interested in. It was away from there. Turns out that it's now the front line of climate change. So would you expect that those atmospheric temperatures have had an effect on the sea ice, for example? Well, this is a sea ice in the Arctic. What I did was work out the sea ice on the 10th of September every year from 1989 to 1993, which is the shaded period on that picture, and it's that yellow picture. And this is the sea ice on the same day in 2018. If I take the two away, everywhere in the picture on the right that's red is where there's substantially less sea ice in the Arctic compared with just 1989 to 1993. That means that larger parts of the ocean are exposed to the atmosphere than were before. Things that were polar seas are now becoming marginal seas, and ecosystems are changing. We know that the ocean's heating up. This is a famous image from 2013 from satellite data, which showed basically a heat wave in the ocean in the Arctic. And it's been similar things going on for the last few years as well. So the sea ice is decreasing in the Arctic. If you look at Greenland, through some fantastic satellites called GRACE, which measured the gravity, the picture on the left-hand side shows how much ice is coming off of Greenland. 255 gigatons. A gigaton is 1,000 million tons. So the ice is decreasing in the Arctic as well. There was an article in Nature which talked about glaciology on climatology on thin ice, and I wrote on Twitter that the bit I did my PhD on had already melted. Before I knew it, I ended up on lots of media things, but the story didn't really turn out how I expected. They thought it was some sort of career thing that was a problem rather than it was about the climate. But we're not responsible for how they spin it, I guess. So that's the Arctic. In the Antarctic, the Southern Ocean is warmed up. The Antarctic is different. Greenland has been covered in ice for about the last 3 million years. The Antarctic has been covered in glacial ice for about the last 30 million years, so quite different systems. But we know the ocean has warmed up. That warming up is going to affect the amount of carbon that's being sucked out of the atmosphere. That ocean warming up has meant that the krill are moving further south. So where they were in the 1930s, around this island of South Georgia where the whaling station was, they're heading south towards the Antarctic continent. The signal of climate change hasn't really reached the sea ice yet. The sea ice around Antarctica at the moment is more variable, but it's a complicated story. I've already shown you this slide, which is the melting around Antarctica and the place where I went. If you look at the yellow box, if you break it down by decade, 79 to 89, 89 to 99, 99 to 2009, you can see they're getting bigger and bigger and bigger, the red things. And around Antarctica, it's also losing mass as well, about 94 gigatons per year per decade, and it's significant. On the Antarctic Peninsula, what were great ice shelves when I started my career have already gone. That's a famous one, the Larsen Sea, which is Larsen B, which is collapsing quite quickly. And the most recent bit of work that I was doing was involved in the sea level rise around Antarctica. And I'll come back to this. Our most likely value was about 45 centimetres of sea level rise from Antarctica. We got asked an interesting question this year by the Foreign Office. What's going to be the effect of climate change on the British Antarctic territory? Which is a really interesting question. We wrote it up as a report and published it as a paper, got together as a fancy infographic. This is on the stand outside, which you can collect. But I can't do better than what the BBC said. Climate change at the Antarctic Peninsula can still avoid irreversible change. Don't ask me to define irreversible at this stage. So it was a backwater. Now it's not a backwater. It's kind of the front line. So I was wondering how to finish up. And of course, I can't really not finish up without Sir David. Last week, he stood in front of a parliamentary committee and he was asked outright that question. What would you wish you'd have talked up about how the climate is changing earlier? And he gave a really interesting answer. We didn't know. 50 years ago, it seemed inconceivable. I didn't believe we could change the climate. Sir David didn't believe we could change the climate, but it was 1938, a British guy called Callender who first linked carbon dioxide to increasing atmospheric temperatures. I'm kind of a bit disappointed to say I didn't 50 years ago. I was very young, obviously, but it took me a while to figure it out. So if we look back at this picture of carbon dioxide, this is when I was a kid out playing in the snow in my garden at the foundation of the Open University. That was when I was thinking I was a climbing hero in my undergrad degree, and you can see how much carbon dioxide in the atmosphere has increased. It took to there before I suddenly realised, working in the Arctic, what our carbon dioxide going into the atmosphere is doing to the polar regions. And now, at this stage in my career, I find myself explaining to journalists what actually is going on. So in that 50-year period, which Sir David talked about, which coincidentally is the 50th anniversary of the Open University, it's gone up 90 parts per million. If you look at the global sea ice, a couple of days ago, in the Arctic and the Antarctic, if you add them both together, it's about 2.5 million square kilometres below the mean of 1981 to 2010. That's about the area of Greenland, Iceland and New Zealand added together. So is it a miserable story? So David turned around and said, the most encouraging thing that we see is what's happening with the voices of tomorrow, which is a kind of good thing about it. It's kind of hard to be positive about a miserable story. But as the Deputy VC was kind enough to talk about the award, I brought it, and I brought it for a reason. I don't often get it out of the box, probably 2 or 3 times. But the interesting thing about this award is if I put it there, that's about the height that the sea level is going to rise by 2100 from Antarctica. If you were to balance it on the box, and hope it doesn't fall off, that's about the height of sea level rise from Antarctica, Greenland, and thermal expansion that we can expect by 2100. If you look at the mathematics for the sea level rise, then for that level of sea rise, we have to be planning for sea level rise that's as high as me. You've heard of the Paris Agreement, which I'm not going to go into now. If the Paris Agreement works out, then we can take away that box, and it will be that high. So there are everything to play for. And I think I'll come back to that point that Sir David made about the climate, that he didn't believe it could change. And actually, the reason he believes it now is because of mounting evidence. And the mounting evidence has come from the broadcast and the television programs that we've been involved in and working with other researchers around the world. It's not going to be easy, but the OU's got a place in that conversation and is helping broadcast these sorts of things to millions of people. Thank you.
So now it's time to hear from you on any questions and comments that Mark's talk has raised for you. And I really hope somebody's going to ask you about being bitten by a penguin. So Mark, I'm going to ask you to come and join me in the seating area, and the information is on the slide for colleagues that are watching us online.
So I'm Stephen Peake from the Open University. Mark, you said in your 50 years that atmospheric concentrations had gone up 90 parts per million, the same time that we're celebrating the 50th birthday anniversary of the OU. Is 90 parts per million a big deal?
So there are people in this room who will know the accurate numbers, probably the person next to you, but you can nod if I get this wrong. It's now higher than it's been for at least the last 3 million years. Shaking his head. Say? Oh, right. So I showed ice core data. We know that carbon dioxide in the atmosphere is hugely important, and other greenhouse gases in the climate of the planet. And there was a natural cycle that was going on. Humans, we did our thing, and over the course of civilization and the Industrial Revolution, we've changed that balance quite a lot. So it might not sound a lot, but it's hugely important. And if we're talking about a planet, you don't have to change things much over a large area for it to add up, and it's taken a few hundred years. Sea level rise at the moment, the result of sea level rise from this increase in concentration is you might think not very significant. In 2100, we're heading, if it works out to the height of that trophy, by the time we get to 2200 or 2300, which you might think is quite a long way in the future, it could be several meters, which, as if carbon dioxide doesn't reduce in our atmosphere.
Quite sobering. So I think we've got a hand up at the back. Did I see a hand at the back there? Oh, one over here.
Thanks, Mark. So Claire Warren, Open University. Have you ever been bitten by a penguin? And if so, when? And what did you do to make it bite you?
Thank you, Claire. It's made my night.
So most Antarctic bases have to be placed on bare rock. And bare rock happens to be the place where most penguins live. So if you're unloading things and you're carrying a large box, it's very difficult not to walk through a penguin colony. And some species are really quite spiteful. And yeah, don't ask me to the name, and that would be cruel. But yeah, so I was carrying boxes through a penguin colony, which you might say was, deserved it, but there was a base to resupply. So but yeah, they look nice at a distance, kind of like polar bears. You don't really want to go anywhere near them. But at least in the Antarctic, you don't have to carry a gun.
At the back there. Thank you. Have we got some online ones too? Great. Start up here.
Dave Rothery, STEM. Mark, when you arrived, we had an oceanography course which taught about sea level rise and CO2, and the plug was pulled on it. What do you have to say about the shape of our curriculum? Can we do it all through outreach and TV, or should we be teaching this mainstream as well?
Pulling the plug is pulling the plug is quite a good oceanographic joke, really. There were a lot of, when we say pulling the plug, that course stops. Other content from that course reappears in other courses and in a modern way. Me personally, would I like to see an oceanography course? Hell yes. But I'd also want to see a polar one as well. But I'm confident that the science is taught in our courses in environmental science and the impacts of how we're changing our climate. I can present the same arguments about what I'd like. Thanks for that one.
So we've got a couple of online questions. We have a mic at the front. Thank you.
So this has come in on live stream, and it's from Andrew Southworth, Associate Lecturer, STEM. Mark, the slide you showed of the icebergs, how much of that increase is down to improved technology and how much is an actual increase?
So this is, I'm assuming the increase in numbers of icebergs from Antarctica. It is definitely an increase in resolution of the satellites that's picking them up. In the old days, when the data set first started, they were quite poor satellites. Now, the satellite data is meters resolution and quite astonishing. But the ones in that graph were actually the giant icebergs. Has there been an increase in giant icebergs coming off Antarctica? We can't say yet. But we can certainly say that over the last 40 years of our record, the ice that's in contact with the ocean is melting more rapidly than it was when we first visited. So satellite science is to blame for that, in a good way.
And we've got another one online.
So this one's coming in from Twitter from Dr. Tamsin Edwards. And she's got a Polar Island Discs question, which is, if you could choose a single one of your trips and fieldwork as your favourite one, which would it be?
Good question.
I can't give one. I'll give two. The Arctic for going with Sir David. I mean, that's a thing that would be amazing. And my trip in 2007, where I spent a few months going around the ice shelves that were melting very rapidly on a ship in just a small team as Antarctic autumn and early winter. So it was bitingly cold and beautiful. But yeah, I thought it was going to be about music. It would be Michael Nyman if anyone was interested in that. But yeah, so two, one for each hemisphere.
There's another one in the room at the back. Thank you.
Robert Cumming from Buckingham. Thank you very much for such an interesting talk. You quoted David Attenborough saying that he didn't know 50 years ago, but was encouraged by the fact that as electorates become more educated and aware of the problem, they will become more proactive and therefore put pressure for change, isn't one of the problems that, therefore, that the number of governments in the world that are in power because of a free-thinking electorate and therefore subject to influence by them are very sadly in a considerable minority?
So I'm a huge optimist about how things are changing in that way, and from 2005 to 2010, getting people or newspapers to acknowledge how much things were changing in the Arctic and the Antarctic was very hard, and now people are listening. We made an Open University BBC program called Are We Changing Planet Earth in 2007 with Sir David, and when they did the program this year about climate change with Sir David, he said, he made the point of saying this is the first time in over a decade. Watching the one that we co-produced in 2007 compared with the one now, the interesting thing was the messages in it are virtually identical. All that's happened is the certainty with which the predictions are made are getting much more accurate, which is, so yeah, I mean,
which I entirely accept that, but that does that apply to, to how many countries around the world does that apply? Does it apply to China, for example? Does the China government listen?
So again, there'll be people in the room that have a better view. I'm sure they do, because governments are planning on time windows of 50 to 100 years, and it's something they're going to be aware of. The question about which country takes most active steps to reduce carbon going into the atmosphere, there is a historical burden. Actually, the David Attenborough committee meeting is worth listening to, because he points out that Britain is a wealthy place because of the Industrial Revolution, and it's not right to, there has to be some equity, coupled to the additional thing of things that we produce or that we have in this country now are produced abroad. So other people are burning carbon to make things for us too, so embedded carbon. And so it's fantastically complicated. What I am certain of is that in the IPCC and other researchers, those sorts of things are being really addressed, which is how you can come up with things like the Paris Agreement on how to limit climate change. But it's the front line. It's the hardest problem now, I would say.
So we've got several more questions in the room, and I've got no idea whose hand went up first because I wasn't paying attention. But perhaps we can start there and work our way forwards.
Thanks. Kedmiel Messick, OU. Mark, you very clearly showed the interesting contrast between the Arctic and the Antarctic, the ocean, the landmass. But there's another interesting contrast between the two, and that's the geopolitical situation. And the Antarctic is very unique on this planet as being the landmass that no country owns as such. We already see the countries in the area of the Arctic positioning themselves for the resources that are going to be opened up as things are changing there. How vulnerable do you think the situation is in the Antarctic? Because we know there's probably a lot underneath that ice as it's getting exposed.
So we could argue about who owns Antarctica. As a British person, naturally, I think a large part of it is a British Antarctic territory. And New Zealand have a. Antarctica in 1958, there was the Antarctic Treaty System that was put in place. And the Antarctic Treaty System is a remarkably robust way of governing the continent. And now that's in a huge treaty meeting that happens every year. And the paper we talked about in what will be the effect of climate on the Antarctic Peninsula, which is British Antarctic territory, went to the Antarctic Treaty meeting this year and was presented to other governments to discuss formally about climate change with Antarctica. And it's the first time that those messages have been received in that international forum. So it's a huge way of getting impact into science. How it's governed, it's not free. I also would say that in 1991, 1992, the environmental protection laws in Antarctica were far in advance of what we saw in the developed world, because it didn't have the historical baggage in setting something up. But it's perhaps a future point of tension, how things will change. In the Arctic, because it's owned by nation states, then and the sea ice is decreasing, access to those regions is going to change a lot in the near future. And we're seeing a lot of investment from countries like Canada and Russia and America in all of them, all 8 of them, in defending their territories, as you would expect, we would.
So I'm aware that we are theoretically out of time, but there's still a lot of questions, I know. Can we take a couple more? Yeah, let's carry on. Come on, it's too good to stop. So there's one here.
Hi, Mark. Phil Sexton, STEM faculty. So you mentioned that the Southern Ocean around Antarctica absorbs a lot of carbon dioxide from the atmosphere currently. Do you know how much it has helped lessen the observed, 90 ppm increase in the last 50 years? So roughly what extent might that 90 ppm increase have been even more had the Southern Ocean not been doing its job? And I guess, do you think, I'm not looking for an answer to the nearest ppm, but and do you think that
so this is
and do you think it will continue to keep bailing us out of our CO2 problem into the
one of
this century?
the programs that I work with the Natural Environment Research Council on is called ROSES, the role of the Southern Ocean ecosystem, and it's about the carbon orchestra as well, which is the ocean circulation and regulation of climate. And those sorts of questions are exactly what they're working on. It's a really straightforward question. Unfortunately, where most of the carbon is being drawn down to the ocean is historically a place where ships don't go, so we don't know much about it, which is why there's so much field work going on. Perhaps a way to look at it will be looking at ocean sediments and looking back in time and get a bigger view, which is what deep sea drilling into the mud on the seafloor will do. But I don't know that answer. I know who I'd ask, and I'm sure that they would say, good question as well. Thank you.
So there's some over here.
My name is Nicholas McCart. I'm from the OU. I remember really clearly the ozone layer and CFCs and my fridge and all of that. I haven't heard about that for a long time. Did that have an effect on the data that you were showing? And has that problem been solved and we don't need to worry about that anymore?
That's good. So I mentioned several times that the Antarctic was complicated. And part of the reason it is complicated because it's isolated. The partial recovery of the ozone hole around Antarctica is changing the winds around Antarctica, which is affecting the sea ice. And we know the sea ice in the Arctic very well. We know the extent, how much there is. We know how thick it is. In the Antarctic, we know how much there is, the extent, but we don't know the thickness because of the physics with the snow is a bit more complicated. But we do know that the winds caused by the ozone are moving the sea ice more. And people have linked it to ecosystem services as well. But the one thing with solving problems is great, and it's a fantastic example. But there were a couple of really good pieces of research over the last few months which demonstrated that CFCs are still being produced in manufacturing in China for fire retardants and things like that. So the fact that it's not recovering as quickly as it should can be detected in those measurements. But yeah, it is recovering, but it's still a place where you get sunburn very easily, particularly if you have hair like mine.
So we had one other question on the row here.
I'm curious to ask about what is the danger of methane gas release from permafrost in the tundras, which could compound to the CO2.
So I've talked about greenhouse gases and carbon dioxide. Methane is a much more potent greenhouse gas, and in the Arctic, the tundra is releasing methane, and there are methanes in the seafloor in the Arctic. I think I've seen lots of things to suggest that that's not going to be released, but the release from the Arctic tundra as the permafrost retreats, which we know it is going to speed up the sea level rise, and it's going to speed up the increase in temperature. And there are all sorts of weird things going on in the climate as well, because things that we try to fix make other things worse. So for example, shipping, there's a new code coming in with shipping which is going to filter out particulates from ships into the atmosphere, which is going to improve air quality. But if you're taking the particulates out of the atmosphere from ships, that means that more solar energy will come straight down into Earth rather than be reflected back out into space, which will increase temperatures. So those sorts of things. But methane is a huge concern, and the permafrost is melting.
So just a last chance to thank Mark for an absolutely excellent lecture.